Hello and thank you for joining us here today. Our project is called Smart Process Planning for Inspection. Here's our team: Zachary Cobb, a Senior Director in Technical Operations for Hexagon Manufacturing Intelligence; Dr. Sodi, a Professor for the Industrial and Systems Engineering Department at URI; and Brendan Smurbeck, a Senior Software Engineer and recent alumni for URI. For the Capstone designers, we have James McHenry, a computer engineer; myself, Juan Corona, computer engineer; and Patrick Miller, a industrial systems engineer. So here's an overview of Hexagon, the company we have been working with over the past year. They develop and create coordinate measurement machines, also known as CMMs, and they are known to be a world-class leader in quality control solutions for manufacturing companies. The image below is a screenshot of the cloud-native asset management software they provide called SFX, which focuses on providing an overview of utilization and downtime for all assets. Our project motivation. So our project motivation consists of these three images. SFX, which is a cloud-native asset management software, focuses on providing an overview of the utilization and downtime for all assets. Second is the Schedule Manager's job list, which consists of X amount of jobs and each job having X amount of parts to complete. The schedule managers are consistently trying to minimize the backlog of work. This is to decrease the downtime caused by job switching, part setup, and breakdown time. So every morning, the manufacturing companies qualify all of the probes. This takes about 1 hour to complete for all tips. As shown to the right, the probe stylus may have more than 2 tips attached to it. Each probe tip has to minimally get 12 points to qualify the precision and ensure preciseness for all measured parts. The anticipated best outcomes is to develop an algorithm or method to solve and give insight to one or more of these topics. Ideal frequency of probe calibration intervals, which is how often should you calibrate the probe tips, and do you need to calibrate them whether or not you use them throughout the day, along with advantages of using an automated tempo CMM, as shown in the figure, which can pick up and place parts and start measuring the routines on its own. So was the ABO achieved? Yes. Started off with the CMM, we used a script that would obtain exact timing of when the CMM switch is tasked, along with the SFX software data output that provides reports of all probe stylus configurations and their data. No actual data of the routine is stored. This is to ensure confidentiality for their clients. And just like the manufacturing companies would, we created our own weekly schedule to run certain routines and analyze any patterns that we could find involving the probe tips calibrations. The economic impact for the company is to provide new features for SFX. This will in turn increase the volume of CMM sales, since we could adopt this solution to other problems given other assets. The question we are solving has yet to be answered throughout the industry of knowing the frequency of when to qualify probe tips. Here is an overview of the team accomplishments. We will go in further detail how we divided and conquered these achievements. Next up is my partner in crime, James McHenry.
Hi, my name is James McHenry, and what I'll be discussing is really what we did the majority of the first semester, and also what I carried on designing tests later on into the second semester, and discussing how we designed our routines and what routines really are. So, what are routines and how do we make them? The basis of making a routine is done through PCDMIS, which is a system used to control the CMM. And what we do to make a program is, in combination with the teach pendant and PCDMIS, we can construct features. How this is done is we'll use the teach pendant to jog the machine over to our part. If we take 3 hits on a flat surface, then it can be sent over to PCDMIS as a plane. with the known coordinates. And usually what you'll do for manual alignments is do that 3 times on 3 axes so we can determine its rotation and where it is in space. Also, for PCDMIS, it's able to run basic script for flow commands, which we do get into when we are designing the later tests that we do for decalibration. We'll use a lot of subroutines, if statements, and other flow commands like that. So for the beginning half of the semester, all of us in our team decided that we should all learn a little PCDMIS, so that way we can all have a basic understanding of how to work with it, as to it's going to be a majority we're going to have to use for this project. The software will be prevalent throughout, and it was very good that we all learned some of it, so that way we'd have a decent idea of what we were doing. For the part I designed was the box with holes that you can see on the right. Pat did the gasket part, and Juan did the table part. All these parts we used were for a job schedule, which we'll talk about a little later. And what this job schedule was is us just using these parts to make a basic measuring setup and run it like you would in a workplace. And for my part, what I did is I would manually align it by hitting the front surface, the top surface, and the right surface, which would get us the rotation and also where it is in space. And then it would go into DCC, which is once we align the part and know where it is, we can put the machine into direct control from the computer. And I would already have placed where these holes would be from the rotation, and what it's going to do, it goes into the holes inside the part and measures them really quickly. And you would do this in a workplace to check, is the tool that's being used to make these holes, wearing? Is it, missing by a little bit? Is this hole a little too big, a little too small? It would check to make sure how round it is and stuff, which is important to know stuff about your tools and how stuff's coming off the production line. On the left here, we can see a probe calibration, and this would be majority of what we focused on later on into this project. And what you can see here is that the probe's touching this known sphere, and this white sphere is a known diameter, and it's been qualified by Hexagon. And what we do is we take the probe tip, and the most unknown part about the probe tip is the ruby itself. So what the machine does, it takes multiple hits throughout on this known diameter, and it back calculates where the ruby is and how big the ruby is on each hit, and this would give you a deviation of how much the measurement is off and how much the ruby varies a little bit. And this is important, as when you're continuing to use the machine over time, the ruby and everything will slightly be moving just from all the sway. The coordinates will be slightly off. So for decalibration testing, which is what we mostly focused on near the end of our project, what we would do is we assumed that hits was our major factor in how the probes would come out of calibration. And how these were designed is we would take this one tip, and at multiple angles, as seen in the video here, we would choose a random angle and then run that angle, and we would do 300 hits on however planes we're going to do for that test. And the tests are determined in a random order, so we could do 2 planes and it would do 300 hits on the 2 planes combined, so it would do 150 on one, 150 on the other, and then it would do a qualification. What a qualification does, it checks against the calibration file, and it checks, okay, how far has this moved in space from when it previously calibrated? And then we record that data down and log it, and we repeat that 17 times. And after those 17 times, we would then switch the angle and the number of planes we're doing, and then we would run all the combinations possible for that. So that would come out to about 12 tests total. And these tests, each one would take about 8 hours, so we would be around 4 days when we're done with all of the tests entirely.
And now we're going to pass it back to my partner, Juan.
Next on the roadmap is the data collection or data combining. Here's just a quick overview of the probe deviations. The first is the standard deviation and the probe radial deviation. These are error calculations taken by the CMM. They're measured by using the calibration sphere to see how far off the CMM thinks the center point is compared to the actual center point. The system's rotary head may move freely in the x and y coordinate, as denoted as the letter A, along with an angle in the z-plane denoted as B. Next is the parsing of the output files. These consisted of JSON, text, and CSV files. The text files, however, as shown in purple, had a complex layout and needed an algorithm to parse out the specific data portions that we needed. As shown below, collecting the probe tip and the error values, I also included a probe ID, test name, and a test run to each of these reports that SFX produced. This was used by the Python library called pandas. So since these files contained over 10,000 lines of code, we needed to get this done at a consistent time. This was to help out down to the right, the learning curve, which shows an operator A, which is a color, can perform a new routine at a consistent rate after X amount of runs. Down below is an example of using the parse data to get the time intervals between each routine. This was to develop the flowchart model, where it starts off at the top with the customer routines and looks at the redundancies of probe switching. Because each routine may or may not need to change probes, the ordering of how these routines were completed could impact on the amount of time spent overall. Next is the optimizing the tool rack of the probe positions. This indeed will just save less than a minute, however, over time and over a year can save a lot of time. So this is to develop the initial work schedule. Next, we would compare the current OEE and see if there's a potential gain. If there is, then we would optimize the job completion order, which is based on the learning curves, and specifically how many routines can an operator perform at a consistent time. Now this is key for the schedule managers because when putting the amount of jobs that an operator could do, it is better to have a consistent rate for the end time. And then that's would go on to optimizing the schedule. Next up is my partner, Patrick Miller.
Hi, my name is Patrick Miller, and I'm going to be going over the key parameters for optimization and how we improve the OEE and the overall throughput of the system. So to start off, I want to talk about the actual OEE comparison. So OEE is split up into three different variables, which are availability, which is how often the machine is available to actually use, the performance, which is how quickly you're completing a task based on a standard time, and the quality, which is how many completed jobs you do compared to how many jobs fail. As you can see from the image below, the system of Smart Factory has a calculator for every single one of these variables. However, we saw some contradictions within the variables themselves. So for the first image, with the 13% overall efficiency, we saw an issue with the availability and how it was calculated, because on one hand, we noticed that it could be possibly run based on idle time, which is the bars in yellow, or it could be based on the error itself. So if it's based on the bars in yellow, then we wouldn't have an availability of 100%. We would have an availability of around 85%. Although if we had the 100%, it would be more close to the error. However, this does not follow the same case in option 2, where we have the large yellow bar, which takes up a large portion of time. In this case, in image 2, we had the issue of the program itself ran, and then we entered a hard crash, which means the CMM itself enters a off state. But instead of calculating it as an error, it calculates it as an idle time. So there's not really any indicator of when the machine is actually up and running again. We feel like that this could be due to how the machine collects this data is primarily through the remote and not the CMM itself. So we feel like a way to include and help with this is to have some sort of indicator on the state of the machine itself along with the actual operation of the machine. So after we ran some actual tests with decalibration, we decided to test 3 main variables, which is the tip angle, which is how the radial angle of the tip going anywhere between 0 and 45 degrees. The number of planes we did, so that was either 1 plane, 2 plane, or 3 plane, or the knuckle angle, which is anywhere rotating the actual body either 0 or 90 degrees. These variables are also recognized as A value and B value within the actual testing, so we've used both. So the first analysis of variance, we tried to test on what variables have the highest impact. This is based off of a regression model of our PR error and how it changes over time. As we can see from the p-value of 95% confidence interval, nearly every value is significant in actually the change in the regression model, except for the actual combination of the tip angle and knuckle angle, with the knuckle angle having the closest significance. However, we wanted to also test how the data spreads within the regression model, so we decided to do a difference between PR error, as seen in the second image. And in this case, we had very different results, having primarily the planes actually affect how the data spreads over time compared to the other variables, which really had no significance in the value itself. In this image, we can also see how each variable actually, specific point affects the regression model and the actual error itself. And we can see kind of contradicting things for each one. So for example, the main effect plots for the R squared value, this is the regression model on the left, in which that case we can see a clear change as you add more planes, how more different or how more extreme the error is over time. However, we do see a larger change within the tip angle, with higher being the 0 compared to the 45, but the opposite case with the knuckle error, where you have a very low minimal change, but one is higher within the 90 still. When actually looking at the difference in variables, however, we notice a different trend, showing that the 2 planes compared to the 3 planes actually has very little change, but the 2 planes has a higher change than the 3 plane and how much the spread changes. And the 1 plane is consistently lower, which we have predicted in the past. We also found that in these cases that the 0 degree mark has a higher spread of change rather than the 45 and the 90. And this could possibly be due to the actual conditions of the room. The fan overhead could also be pushing the actual tip out of place, which could be causing that as well.
We would like to give a special thank you to everyone who's helped us along in this project. Zachary Cobb, the Technical Director and Senior Director of Technical Operations over at Hexagon. John O'Hare, the Old Product Manager at Hexagon. Brennan Smirmack, a Senior Software Engineer who graduated URI in 2017 and has helped us with organizing and discussing with other parties. Charles Hilton, an applications engineer over at Hexagon that's helped us with our PCDMIS programming. Dr. Sodi, professor for the ISE Capstone, and also assisted us when we did not have direct contact to a new technical director temporarily. And for Dr. Sunak, the professor of our Capstone, and a great help.